Welcome to lecture 2 of module 3 on heat transfer.
In this lecture, we will discuss on one-dimensional unsteady state heat conduction. We will continue our discussion. Here, we will discuss particularly on distributed parameter model, and for that distributed parameter model, we have shown that there are two possibilities. In the last lecture, we have shown there are two things we are going to discuss. One is on transient heat flow in a semi-infinite solid, and another one is for a infinite body. So, now in this lecture we will be discussing on transient heat flow in a semi-infinite solid. Okay. So, this is what we are going to discuss in this lecture. We will see that we will try to develop the mathematical model for this and try to find out with the help of some analytical solution, we will try to find out the temperature distribution, and also we will try to find out that how the heat flow takes place. Okay. Now, let us consider this is a semi-infinite body, and particularly in Cartesian coordinate. Okay. We consider in a Cartesian coordinate the semi-infinite body, and the solid is initially maintained at a temperature of Ti. That is the initial temperature Ti, and then suddenly it is exposed to a temperature of To, which is much lower than Ti. So, suddenly it is exposed to a temperature To, which is lower than Ti. That means, heat transfer will be taking place from the body upon the surface to the surroundings. That is going to happen, and we will see that how the temperature will be function of this body. So, what we will do is, say this is in this direction, we are interested to know the temperature profile. So, this is the x direction, here x equal to 0. Okay. So, according to this, now my initial and boundary conditions would be like at x equal to 0, this is the boundary condition. At x equal to 0, we can understand that T equals to that this surface is suddenly exposed to To. So, it is To, and at T equals to 0, that is the initial condition, that whole body had been at a temperature of Ti. So, it happens that at x tends to infinity, in this side, the body will have almost the same temperature as Ti. So, T will be equal to Ti. So, this is the condition. So, if I write in the other form, we will write that T at x 0, this is the initial condition, this is equal to Ti, initial condition, and T at 0 at any time t will be equal to To. This is the boundary condition 1, and T infinity t at any time will be equal to Ti, that is the boundary condition 2. Okay. So, this is the conditions. Before solving this, we have to understand what is the governing equation for this problem, and the governing equation will start from general conduction equation. General heat conduction equation, we know the general heat conduction equation is, or the Fourier field equation is, that 1 by alpha del T by del T equals to grad square T plus Q dot by K. Okay. Now, this Q dot gen and heat generation by K, as we have discussed, K is the thermal conductivity, alpha is the thermal diffusivity, like that. And in the present situation, we will assume that Q dot gen is equal to 0, there is no heat generation. In the body. Okay. So, under that situation we should get that del square t by del x square plus del square t by del y square plus del square t by del z square, and that is equal to 1 by alpha del t by del t. Now, as because we are interested on one dimensional heat transfer, and also we are interested in x direction. So, the gradients along other directions will be 0. So, we will have this is 0 and this is 0. So, then finally, the equation is of this kind, that del t by del t is equal to alpha into grad square t by grad x square, del square t by del x square. So, this is becoming the governing equation for the present system, and already we have discussed the boundary conditions, that t x 0 is equal to T I, T 0 I am sorry T 0 x is equal to T O, and T infinity t will be equal to this is T I again. Now, we can understand this is a partial differential equation. Now, this partial differential equation, there can be several ways we can solve this partial differential equation for getting an analytical solution. There can be a numerical solution for that also. We are not interested about a numerical solution for at this moment. We will be discussing about the analytical solution. I will try to see how is the temperature profile for this, and when we will do that, we will assume that there are two independent variables in this particular equation, which are time and x. These are the two independent variables. What we will do? We will go by method of combination of variables. Method of combination of variables for getting the analytical solution of this, and to get the analytical solution, what we will do is we will assume a new, or we will propose a new variable which is independent variable, that is say eta, and that is a combination of the two independent variables t and x, and for this is a very standard way of getting this. So, eta is actually x by 2 root over alpha into t. So, this is one independent variable that is being taken, and interestingly we can see that eta is dimensionless. So, we have taking a new independent variable for this solution eta, which is a dimensionless quantity, that is by coupling the two independent variables x and t is the time. So, we can see that alpha, unit of alpha is meter square per second, and unit of time is second. So, unit of root over alpha t is only meter, and unit of x is meter. So, finally, it is becoming unitless. This is a dimensionless quantity. So, once we have got x as a dimensionless quantity and x and t is combined into a dimensionless quantity, a new variable, then we will write temperature also in terms of a dimensionless variables. We will write first the reduced variables and then dimensionless. So, t will be writing as T I bar by T O bar, and where T I bar is equal to T minus T I, and T will be T by T bar by T O, and where T bar is equal to T minus T I. T bar is equal to T minus T I, and T O bar is equal to T O minus T I. So, this is the way we have now defined two variables eta and t. T is the parameter, dependent parameter, and it is made now I am sorry we will define this one as y. Y is a dimensionless variables of two reduced temperatures T bar and T naught bar. T bar is T minus T I and T naught bar is T naught minus T I. Thus, we have defined two dimensionless variables. One is the dependent parameter which is temperature, which is expressed in terms of capital Y, and independent parameter. There are two independent parameters x and t. They are combined to give a new independent parameter which is eta and which is again a dimensionless quantity. And then if we reduce the boundary conditions, we will see our initially the boundary conditions were like this. If I did write again that t initial and boundary conditions, that t at initial condition means x 0 okay, is equal to T I, and t at 0 t is equal to T O, and t at infinity t is equal to T I again. Now, if we see we have written eta is equal to x by 2 root over alpha t. Now, see that when x is equal to 0 or t x equal to 0, then for any t x equal to 0, for any t eta equal to 0, okay. And then for say x is equal to infinity, or rather if I write for x tends to infinity and t equals to 0, we know that eta tends to infinity. So, two conditions, one initial and one boundary condition, one initial and one boundary condition is getting reduced to only one condition, either x tends to infinity or t equals to 0, eta tends to infinity. Okay. So, these are the situations. So, when eta is equal to 0, t equals to T I, that implies that, and here we know that y is equal to t minus T I by T naught minus T I. So, at for any t, for x equal to 0, t is equal to T O, this implies that y equals to 1. Okay. And for x tends to infinity or t equals to 0, here t is equal to T I, this implies y is equal to 0. Okay. So, this is the reduced form of the boundary conditions. Okay. Now, so reduced form of boundary condition is that eta is equal to 0, y equal to 1, eta tends to infinity, y equals to 0. This is the reduced form of the boundary conditions. Now, if we go back to our original reduced equation that we got, and now if we try to reduce this equation, that del t by del t is equal to alpha into del square t by del x square. After defining the expressions for eta and y, if we reduce this equation into in terms of eta and y, we will see that how it comes into what kind of form it comes into. We will see that. So, to start with, what we will write is that, say we have to get this expression and we have to get this expression converted in terms of y. So, what we will do is, say y equals to t minus T I by T naught minus T I, and then del y by del x is equal to 1 by T O minus T I into, we have got del t by del x. Okay. And we know that eta is equal to x by 2 root over alpha t then we can get del eta by del x will be equal to 1 by 2 root over alpha t. Okay. So, then again we need to get del y by del eta not in terms of x. So, we will get del y by del eta will be equal to del y by del x into del x by del eta. So, that means we are getting 1 by T o minus T I into del t by del x into what we will be getting is del x by del eta is equal to ulta of this. So, we will be getting 2 root over of alpha t. Okay. That means, we are getting so this implies that del y by del eta is equal to 2 root over alpha t by T o minus T I into we will get del t by del x. So, now if we further take away this derivation, then we will get del square y by del eta square, because our interested to get del square t by del x square. So, del square y by del eta square will be equal to 2 root over of alpha t by T o minus T I into del square t by del x square into del x by del eta. So, this becoming now 4 alpha t by T o minus T I into del square t by del x square. So, we can write now. So, del square t by del x square is equal to T o minus T I by 4 alpha t into del square y by del eta square. So, this is one conversion of del t by del x is converted into y and del square t by del eta square y and eta form. Then there is another terminology, that is del t by del t. So, what we will write is that t minus T I by T o minus T I is equal to y. So, we can write 1 by T o minus T I into del t by del t will be equal to del y by del t, but we are not interested only in del y by del t, we are interested on del y by del eta. So, this will be equal to del y by del eta into del eta by del t. Now, we have eta is equal to x by 2 root over alpha t. From there we can write del eta by del t is equal to minus x by 4 root over alpha into t to the power 3 by 2. This can be written as minus x by 4 t into root over of alpha t, and that is we will write as minus eta by, again we will replace eta by this, eta by 2 t. So, what you can then write that del t by del t will be equal to minus eta into t naught minus t I divided by twice t into del y by del eta. So, now if we replace all these in the basic equation, basic reduced equation, then we will get 1 by alpha del t by, if we write this 1 by alpha del t by del t is equal to minus eta into t naught minus t I by twice alpha t into del y by del eta. Now, if we reduce these values of this form and the previous one, if we replace in the original equation, then we can get the del square y by del eta square plus 2 eta into del y by del y by del eta equal to 0, and as we know that eta is now, the y is a function of eta only. So, it is only one variable. In that case, we will write that del y by del eta as a perfect differential in place of writing it as a partial differential. So, we can write now d 2 y by d eta 2 plus twice eta dy by d eta equals to 0. So, this is the reduced governing equation for the present case whatever we have taken up. And in this reduced governing equation, we have got the boundary conditions already decided for this case, and these boundary conditions we got when we have assumed that the whole body is suddenly placed, that left face of the body is suddenly placed to a temperature T naught, which is lower than the temperature of the initial temperature of the body. Okay. Now, if we solve this equation, then we will get the solution of this equation. If we try to find out that d 2 y by d eta 2 plus twice eta dy by d eta will be equal to 0. This means that d eta of, okay, if we write that from this we can write that ln dy by d eta is equal to C 1 minus eta square. We write it as C 2 e to the power minus eta square. Okay. And then we can write that y is equal to C 3 plus integral C 2 e to the power minus eta square d eta. So, this is the solution. So, we can write this as like this C 3 plus C 4 error of eta. So, we will introduce a function that is called error function. Okay. We will introduce a function that is called error function, and then how it is, error of eta, error function eta is equal to 2 by root over pi integral 0 to eta e to the power minus eta square d eta. You can understand that this expression is difficult to integrate. So, therefore, one function is given, is called error function, and there will be different values of error function are tabulated in different literatures for different values of error function. We can find out the value of the integral based on the different values tabulated in the literature. Okay. Now, we have to put the boundary conditions. Here we will say that there are two boundary conditions. So, the first boundary is for eta equals to 0, error of 0, and that is equal to 0, and then y equal to 1. Okay. For eta equal to 0, error of 0 is equal to 0 and y is equal to 1, that we have seen already, and for eta tends to infinity, error of eta equal to 1 and y tends to y equal to 0. Okay. So, this is what y tends to 0. Thus, putting the boundary conditions, we will get that in the very first, putting the first boundary, if we say this is B C 1 and this is B C 2, but putting first after B C 1, if we put the first boundary conditions, then we get that 1 equals to C 3 plus 0, this implying C 3 is equal to 1, and then if we put the second boundary after B C 2, if we put second boundary, then we get that 0 is equal to 1 plus C 4 into 1. This implies that C 4 is equal to minus 1. So, we can get the solution to be like this, that y equals to 1 minus error of eta, and this is written as, so therefore, we can write t minus T I by T naught minus T I, and that is equal to 1 minus error of x by 2 root over alpha t. Okay. So, this gives the temperature profile when a semi-infinite solid is there and its one surface, which is the transferring heat, that is suddenly subjected to a constant temperature of T naught. initially the temperature was Ti. Okay. Now, if we try to know the heat flow, so heat flow at any position from the solid body, we know that by conduction, because from the solid body we are telling. So, q dot x along x direction will be equal to minus k into A into del t by del x, that we know, and in this case it will be we can find out that del t by del x in this case is nothing but minus T naught minus T I by into 2 by root over pi into del del eta of 0 to eta e to the power minus eta square d eta into del eta by del x, and this one actually minus T naught minus T I into 2 by root over of pi into e to the power minus eta square. So, the derivative is integral and derivative cancels each other. So, it is becoming minus eta square into, and del eta by del x term is, and we have seen already 2 root over of alpha t. So, this gives equal to minus T naught minus T I, okay, by root over of pi alpha t into e to the power minus eta square. Now, if we are interested to find out the del t by del x at x equal to 0 or q dot x at x equal to 0, so del t by del x at x equal to 0 will be equal to minus of T naught minus T I by root over of pi into alpha into t. So, we can write that q dot x at x equal to 0 equals to k into area into T O minus T I by root over of pi into alpha into t. Okay. So, as we understand that as because T O minus T I is a negative quantity, so the heat will be flowing from the wall to the surroundings. From the figure you can see that heat will be flowing from, this will be the direction of heat transfer from wall to the surface. So, q dot minus x, this is the direction of heat transfer. Okay. So, this is the temperature profile and heat flow rate that we can find out. Now, there could be some other cases when the situation will be little bit complicated and solution of that kind of problem will be further complicated. The other cases means in the present case what we have told that a semi-infinite body that is subjected to that one phase of this body is subjected to a temperature T naught, which is maintained at constant temperature. It need not be the case. The cases could be that there is a constant flux condition. The case one, other cases will be say constant flux at x equal to 0, that is one case, and other cases, another case could be the variable flux at x equal to 0. So, these are the two different cases can also be there. Whatever we have conducted, we have carried out at this moment is that, so if I say here case 2 and this is case 3, we have considered on the case 1, it says constant temperature at x equal to 0, which is basically T naught, that we have considered. This case already we have seen now, but there could be two more cases, constant flux at x equal to 0 and variable flux at x equal to 0. So, once we do this, then the boundary conditions are going to change. So, if we say from in terms of t and x, so for case 2, t at x 0, okay, will be equal to T I, that is the initial condition, and then t at x equal to infinity and any time t, that also will be equal to T I. So, there is no problem, these are not going to change, but what is going to change is that at x equal to 0, what happens to the boundary conditions? At see, if you see again that t at x 0 is equal to T I, that means this is the initial condition and this is a boundary condition 2. Boundary condition 2 is also remaining the same, because the body is infinite in the direction of x. So, what is happening at infinite direction, there is, it is more or less like your initial temperature is not changing much. At that place the temperature is not reached, change of the temperature is not understood, and the other condition, which is the boundary condition 1, that is going to change, and there the condition will be like this, that minus k into a into del t by del x at x equal to 0 for t greater than 0 will be equal to a constant value. Q naught is the I am sorry, we will say Q naught, that is the called constant heat flow rate, or we can say that minus k into del t by del x at x equal to 0 for t greater than 0 is equal to q dot naught by a, this is called constant heat flux. So, this whole amount is nothing but the constant heat flux condition. So, under this condition it can be shown that the solution will be further complicated. However, I will not go further solving this, I will just write down the expression of the solution. The solution becomes like this, is T minus T I equals to twice q dot into root over of alpha t by pi by k a exponential minus x square by 4 alpha t into minus q naught q dot naught x by k a into 1 minus error of x by 2 root over of alpha t. Okay. This is just for the understanding of the how the solution look like, okay, for this kind of situation. This is pi, if I write in a better way. Okay. Now, the case 3, there is the variable boundary condition, variable flux, heat flux is varying. How is it? So, at x equal to 0, h is the convective heat transfer coefficient, A is the surface area, into T infinity is the surrounding temperature, minus T is the temperature of the solid body at x equal to 0. So, T infinity is temperature of environment, okay, and at x equal to 0 should be equal to minus k a into del t by del x at x equal to 0. Based on these boundary conditions and the other two boundary conditions are remaining the same, it will be t at x and 0. This is the initial condition, that should be equal to T I, that is the I C, and other boundary condition is t at infinity and time, any time t, and that is infinity, again it is T I. This will be the one boundary condition 2, this is the second boundary condition, and this becomes the boundary condition 1. So, when we have this kind of boundary conditions for case 3, then the solution of the above equation becomes like this, that T minus T I by T infinity minus T I equals to 1 minus error of eta minus exponential h x by k plus h square alpha t by k square into 1 minus r of eta plus h root over alpha t by k. So, this is the solution. So, through this we just try to highlight that the solution is becoming complicated when you have more complicated boundary conditions, but point is that probably that boundary condition is the more realistic boundary conditions. This boundary condition, whatever I have discussed, is the more realistic boundary condition, because we can have in many situations we will have a variable heat flux condition at the boundary that we generally observe. So, if that is a more realistic boundary conditions, but the solution is little bit complicated, and this may be exercise, this may be tried to get the solution of this kind. Okay. Now, we have discussed through this lecture, we have discussed that what happens to the temperature profile when there is a semi-infinite body and heat transfer is taking place from the body to the surface to the surroundings, and when there are three conditions are maintained, constant three conditions are maintained the one surface of this body, which is either at constant lower temperature or at some constant flux, heat flux condition, or maybe a variable heat flux condition on that surface. And we have shown that in that case the basic general conduction equation has to be taken, and this general conduction equation is to be reduced into the form of one dimensional heat conduction unsteady state heat conduction equation, and then this reduced equation, which is a partial differential equation, is to be reduced to an ordinary differential equation. This is one method of solution where the combination of two independent variables are giving rise to one independent variable. As a new independent variable is being generated, and then the partial differential equation is converted into a single ordinary differential equation, and then this ordinary differential equation with the reduced boundary conditions are being solved. We have shown the solution for one particular case, but for other two cases, possible cases, the solution has been written, and how the solution is coming is a little bit complicated. The students or interested persons may carry on and find out the solutions for this. Now, what I will do is I will take up a problem in this, particularly considering the constant temperature condition. So, the problem is like this. A large block of steel K is equal to thermal conductivity, K is equal to 45 watt per meter per Kelvin. Then alpha is the thermal diffusivity, and that is equal to 1.4 into 10 to the power minus 5 meter square per second, is initially at 800 degree centigrade. Okay. Its surface is suddenly exposed to a constant temperature of 30 degree centigrade. Okay. Now, determine A. There are three parts for this problem: temperature, two centimeter below the surface after 20 seconds. B, time required for the temperature to reach 750 degree centigrade at a depth of 1 centimeter. And the third question is time required for the gradient at the surface to reach 10 degree centigrade per centimeter. Okay. That means it is like this. So, we have this surface and here x equal to 0, and in this direction this is the positive x. Okay. And the initially the whole body is at 800 degree centigrade, which is nothing but Ti in our derivation, and this surface, because this is infinite body, this side and this side are infinite, and this side what we are saying, this side is particularly the infinite, and this side the surface, okay, is given a temperature 30 degree centigrade. So, it is a constant temperature and which is nothing but equal to TO. That is what we have been discussing, TO in the our previous case, the constant temperature condition, and this body has got K equals to thermal conductivity equal to 45 watt per meter per Kelvin, and it has got alpha is equal to 1.4 into 10 to the power minus 5 meter square per second. This body has got this. So, what is being asked, that first question is the temperature 2 centimeter below the surface after 20 seconds. So, as we have understood, the temperature in this body is a function of both space as well as time. So, it is being asked that, say suppose at any point here that it is say x is equal to say 2 centimeter. So, at this point what is the temperature of this body after 20 seconds? Initially it was Ti, and then after 20 seconds what happens to the temperature at this point. Then the second point asked, second question, the time required for the temperature to reach 75 degree centigrade at a depth of 1 centimeter. So, the other way around. So, suppose I am sorry. Suppose this is equal to say 1 centimeter. So, now it is being asking at this point what the temperature is given 750 degree centigrade, then what is the time? And here time is given 20 seconds, what is the temperature? That has to be found out. Okay? And the third case is the time required for the gradient at the surface to reach 10 degree centigrade per centimeter. What is that? That is del T by del x. This is nothing but the temperature gradient, or you can say the dt by dx. This is the temperature gradient at this point, and this is the surface. So, temperature gradient at this point has to be seen when it is coming to 10 degree centigrade per centimeter, that is to be seen. Okay. Now, to solve this, in the first case A, we know that x equal to 0.02 meter, t is equal to 20 second. Okay. So, eta is equal to x by 2 root over of alpha t, and this value is equal to 0.02 by 2 into root over of alpha is equal to 1.4 into 10 to the power minus 5. We have to see the units properly, and time is equal to 20. So, this way we got as 0.6. Now, we have to find out the error of eta. So, actually that can be found out from the tables given in the in different text, different references, different text. The values of eta can be error of value function values can be found out, and error of eta when eta is equal to 0.6 is nearly equal to 0.6. Okay. So, just putting this value, what we get, that we also know that T naught minus T I is equal to 800 minus, I am sorry, T naught minus T I is equal to 30 minus 800 is equal to minus 770 degree centigrade, and so T I minus T O is equal to 770 degree centigrade. So, now just putting the values of, we know that T minus T I we have to calculate, and that should be equal to T naught minus T I into T naught minus T I into 1 minus error of eta. So, this implies that T will be equal to T I minus T I plus T O minus T I into 1 minus error of eta, and that we know T I is equal to 800 in degree centigrade plus T O minus T I, now it will be minus 770 okay, into 1 minus 0.6. So, this is becoming now 492 degree centigrade. So, interestingly T is equal to this. If I put T I in terms of Kelvin, then we will get T in terms of Kelvin. So, in this if I take T I is equal to 1073, then we will get T in terms of Kelvin, then we will get T in terms of Kelvin, and that value will become 765 Kelvin. So, we have to be very careful about that. If we put T I in terms of Kelvin, we will get this T in terms of Kelvin. If we put T I in terms of degree centigrade 880, then we will get T also in terms of degree centigrade. So, this is the first part. Then second part B, again we have T minus T I by T naught minus T I, and that is equal to 50 by 770. Okay. The negatives are cancelling each other, and this becoming 0.065, and that is equal to 1 minus error of x by 2 root over of alpha t. Now, what we have to find out? We have to find out the value of time t, and x is known 0.01. So, from there we can find out that x by this is happening error of, this implies that error of x by 2 root over of alpha t, that is equal to 0.935, and that value is coming for error of approximately equal to 1.35. Okay. Then we can get x by 2 root over of alpha t as 1.35, and we know what is x. X is equal to 0.01. Okay. X is equal to 0.01 meter. Okay. Just by putting the values of this, we can find out this expression. So, what we can find now, x square by 4 alpha t is equal to 1.35 whole square. Okay. So, from there we can find out the value of t will be equal to 0.01 whole square by 4 into alpha is equal to 1.4 into 10 to the power minus 5 into 1.35 whole square. So, if we do the calculation here, we will get that t is equal to 0.98 second. Okay. So, this way we can find out the time for reaching the temperature of 750 degree centigrade at a distance 0.01 meter. Okay. And the third part of this problem is that we have to find out, it is being given that dt by dx at x equal to 0 is given as 10 degree centigrade per centimeter. So, this is equal to say 1000 degree centigrade per meter. So, this is very important, we have to be very careful about the unit. So, dt by dx equal to 1000 degree centigrade per meter, and then we have seen that dt by dx in our derivations we have seen at x equal to 0 is equal to to minus ti by root over of pi into alpha into t, and that is equal to 1000. And so, we can find out, and this will be equal to, because it is a in the other direction is happening. So, we will write this a negative, and to minus ti is also is negative. So, we can find out, this implies that pi alpha t will be equal to this difference is 770 by 1000 minus this whole square, and from here I have to find out the time is equal to 0.77 whole square by pi into 1.4 into 10 to the power minus 5, and this value is nearly equal to hours. Okay. So, this way we can find out, this is in hours, because if you do this, it will be huge values in seconds, and then converting this will be getting in terms of hours. So, this will be around. This says that around we are going to get the values of del t by del x at x equal to 0 as 10 degree centigrade per centimeter. Okay. So, this way we can find out that how we can make use of the formulae that we have developed for one-dimensional heat transfer using distributed parameter system, and here also we have tried to show that how combination of variables can be used to get a solution for a simpler boundary conditions. For complicated boundary conditions, it is little bit more complicated, and that can be kept as an exercise for the students who are interested for this. Next class we will be discussing that again that distributed parameter system, where we will be studying the heat conduction problem for infinite body having a specific thickness, for example, a slab or cylinder or a sphere. We will see, and there we will try to take up a different methodology that is called separation of variable methods. We will try to take up and see that how the solution can be arrived and how the problems can be solved for those cases. And then we will take up problems for cases where we can go by graphical methods. We can use charts, available charts to find the solution of certain heat conduction problem, which is unsteady state and one dimensional. Okay, thank you very much.